First up will be Bryan Duncan, who comes with, who's a member of the NASA's Air Quality Applied Sciences team, which has the goal of using satellite data and sort of facilitating it for use by the air quality community. He's a deputy project scientist for the NASA Aura mission, which has been observing air quality as one of its core goals. He uses a lot of different data sets to apply to tropospheric issues, including long-range transport of pollution and air quality applications. He's also involved in the development of NASA's chemistry and climate model, which includes a lot of really large-scale kind of simulations of air pollution and the climate impacts of methane.
Okay, so when people think of NASA, they usually think of outer space, you know, the space shuttle, the recent Voyager flyby of Pluto, but they don't know that there is a whole fleet of satellites orbiting the Earth right now, and they're looking at the Earth. They're measuring it, quite a few different things, changes in ice sheets, ocean currents, and the atmosphere. And they are also measuring air quality. And I've highlighted those satellites that have instruments that measure air quality, various species. As you can see, there's about 6, 7 of them here. A few of these have not been launched yet, for instance, the Tempo satellite, but they should be launched within the next few years. Okay, this is my favorite image of all time. It's not satellite data. It's actually a photograph taken by an astronaut on NASA's Skylab space station in 1973, long before many of you were born, I can tell. And this is an image of Los Angeles in 1973. It was highly polluted, much more polluted than it is today. So this gives you an indication of the type of air quality that I was breathing back in the day, okay? So our air quality is a lot better than it used to be, and satellites are there to show this. And the importance of satellites is spatial coverage. You get this bird's eye view, global coverage. That's the advantage above ground-based networks. Okay, so first of all, what can I do with satellite data? What are the applications? Well, I've listed a number of them here, and I'll show examples in my talk of each of these. We can monitor trends in several air pollutants, such as nitrogen dioxide, a member of the Knox family, sulfur dioxides, carbon monoxide, aerosol optical depth. We can estimate pollutant emissions from individual power plants and from cities. We can track plumes of pollutants, for instance, from wildfires or from China or wherever. We can provide evidence for exceptional event declarations, which several people are doing now. For instance, they can use true color images of smoke plumes in their declarations. The data can be used to support air quality forecasting. We can evaluate air quality models with the data. And we can estimate ozone formation sensitivity. It's very important from the Knox VOC perspective, and I'll show a slide on that. Okay. However, what I just showed you sounds really great, but there are a lot of, while satellite data is very powerful for air quality applications, there's quite a few caveats. So what can't I do with satellite data? Okay, well, you can monitor trends in air pollutants, but you can't do it continuously. Right now, we only have one overpass per day, so you get a snapshot once per day of any specific air quality situation in an urban area. And it's really difficult to measure nose level values. So the EPA's health standards are based on, or standards are based on human health. So we need to get at that nose level concentration. For estimating pollutant emissions, well, we can't do it on a cloudy day. The satellites can't see through the clouds. If there's snow on the ground, like in Wisconsin, it's always a problem. We have to throw that data out. We can't see things at night. For tracking pollutants, we can do that for many of them, except for ozone and many of the important VOCs. And ozone is the holy grail. Many satellite people are trying to get at how to take satellite data and actually observe nose level or near surface ozone. It's a very difficult problem. There's a lot of smart people working on that. And Many of them are optimistic, some aren't so optimistic, so stay tuned on that issue. For supporting air quality forecasting, some of the data is available in what's called near real time, like 3 hours, 4 hours, 8 hours from the time the data is collected. But most of the satellite data is not available in near real time, which makes it a little harder for supporting this air quality forecasting. And also, there's always the issue of spatial resolution. So many, as you know, like with EPA, they have health monitors, say near interstates or near factories. Satellite data, we just can't give you that spatial resolution. I've had people ask me, are you able to use that SO2 data to look at what's happening on Elm Street versus Main Street? No, we can't do that yet. There are some satellites that have spatial resolutions on the order of tens of meters, but most of it's much bigger than that, at least 10 by 10 kilometers or greater. Okay, so here's an example of tracking plumes, of pollutant plumes. Up on the right, we have a true color image of 2 fires that were going on simultaneously, one in the Great Dismal Swamp and one in the Evans Road Wildlife area. And these were in Virginia and North Carolina. And clearly the smoke is associated with the fires, and concentrations of PM, for instance, that were elevated in nearby cities, it's clear that it was coming from these fires. On the left, we have an image of carbon monoxide, and it's from fires in California. And you can clearly see that it's impacting Nevada and Idaho and states downwind. As Arlene was speaking about this morning about stratospheric intrusions, one way that we can't actually see the ozone itself and very clearly these intrusions, but we can see low relative humidity associated with stratospheric air in the lower left there. And we can also use what's called a total ozone column data product. We can look at the gradients, and we've identified that when you have these strong gradients in the ozone column, you have a stratospheric intrusion most likely. Okay. So as I said before, we really can't measure nose level ozone currently, but fortunately we can measure 2 of its precursor species. We do have proxies for those. A proxy for nitrogen oxides, which come out of the tailpipes of cars and out of smokestacks. And we also have proxies for the volatile organic compounds, or VOCs, which come from inefficient combustion of gasoline, for instance. And together these form ozone. Okay, so NO2 can be measured from space, not NO, but NO2 can. And it's a proxy, it's been shown to be an effective proxy from Knox. And this image shows you NO2 levels, I think this was in 2005. And you can clearly see the reds indicate that the eastern US is far more polluted than much of the west, as you would expect. There's far more people in the eastern US, and the cities show up as hot spots. Okay, and for VOCs, we can use a species called formaldehyde as a proxy. And that's because when many VOCs react in the atmosphere, they actually are oxidized to formaldehyde. They go through that in their oxidation chain. And this example shows that on a cool summer day, the formaldehyde levels are actually lower than on a warm or a hot summer day. And this is associated with natural emissions coming from trees. So one of the species is called isoprene, and when it oxidizes in the atmosphere, it forms formaldehyde, and you can clearly see that signal here. And this is very important from the regulatory perspective because it makes more sense to decrease NOx emissions than it does anthropogenic VOC emissions because there's so many VOC emissions from the trees. And for decades now, air quality folks have been using the VOC to Knox ratio as an indicator of ozone sensitivity in urban areas. And so we put together this formaldehyde to NO2 ratio as observed from space, and it is a proxy for ozone sensitivity formation. Look at the circled areas. These are cities. We have Los Angeles, Chicago, New York City. And if you look in 2005, you see a lot more blues than you do in 2013. And this is indicating that because of NOx emission reductions that have been occurring in the U.S., that ozone formation sensitivity is becoming even more NOx limited. So reducing anthropogenic VOCs is not particularly effective at this point. It is in some cases, but overall, it's better to go with NOx. Okay, so of course your eyes were drawn to the big ugly red spot in the middle, and that has to do with 2005 being a hotter summer than 2013, and these isoprene emissions from trees are a function of temperature. So the hotter it is, the more VOCs you have coming out of these trees, so that's why you see such a bright red spot in 2005 and not 2013. Let's zoom in on the northeast U.S. and Southern California, and you can see just how different the ozone sensitivity is between these 2 years for various cities. These NOx emission reductions are clearly working from the NOx perspective, and ozone has been going down over the last 10 years, I think about 15% on average across the U.S. And you can see the same thing for Southern California there. You can use satellite data to estimate trends and emissions. And here are two different species, nitrogen dioxide and sulfur dioxide. And of course, the nitrogen dioxide, because of emissions reductions, have been going down quite dramatically over the last decade, anywhere from 20 to 40% during the satellite record. And sulfur dioxide has also been going down. It's being controlled from coal-burning power plants, and you can see in the Ohio River Valley and into West Virginia and Pennsylvania that levels have gone down quite dramatically, sometimes 90% for individual plants or more. And the satellites give us this great bird's eye view of these changes that are going on in the U.S. now. And we can monitor new sources. So fracking is the new hot topic. People want to know what kind of pollution is coming out of fracking. And this plot shows that, actually shows a percent difference, or an absolute difference for the bigger map, percent difference for the insets. And over the whole U.S., like I said, it's been going down by 20 to 40% over the last decade. But in the areas of western North Dakota and West Texas, you see increases of on the order of 30% in this one pollutant of nitrogen dioxide. And that's associated with the fracking and oil and natural gas extraction that's going on there. And I think what's very interesting, you can see these sources, or these hotspots, these increases in pollution, because they're rather isolated from the urban areas. They stand out clearly in a percent difference map. And this NOx, or this NO2, is associated with two different things, flaring and also emissions from the heavy machinery that's used to extract the oil. And you can even see these from space, these flares that are going on, plus lights associated with the fracking activities in western North Dakota. And this is from the SUMI MPP VIIRS instruments. Okay, so if anybody's interested in anything of what I just said, there are plenty of resources to find out more information. There is the Air Quality Applied Sciences team that's funded by NASA, and there's a number of people that are here at this meeting that are involved in ACAST. So if you're an air quality manager, come talk to us. If you're a graduate student that wants to know more, come talk to us. Just look at the website and check us out. There's also a program called RSET, the Applied Remote Sensing Training Program. And they actually offer free webinars. So if you're interested in using satellite data for your application, not just for air quality, but for, let's say, water cycle or carbon cycle, they actually have programs that you can be involved in. You can get in these free webinars. And there's some review articles out there. I was the lead on one of them that gives a basic overview in rather common language, plain language, easy to understand, on what you can and can't do with satellite data and what resources are available to you. And there's also another one on estimating emissions from, for instance, power plants using satellite retrievals. And we have now a website that has come out, and we're also adding to it every day. So be sure to go to this link here and check it out. We have trends for individual cities and maps and some other cool stuff like a table listing resources that you can use to make your own data plots. So I think that's all I have. Just to conclude, from the energy perspective, you can also use satellite data to estimate trends in energy consumption as well. And people are starting to investigate that. For instance, nitrogen dioxide. Whenever you burn coal or gasoline, you emit nitrogen dioxide, but you also emit carbon dioxide as well. So with our data, which is about 0.1 by 0.1 degree, I didn't show these images here, but we found that you can actually pick out individual power plants and look at their trends over time. And if you make assumptions about what type of coal they're burning and so on, you can estimate a trend in CO2 as well from this. So this NO2 data, this satellite data, has relevance for estimating changes in climate gases with very high resolution. So that's it. Thank you.
Thank you.